of you here. All right. Okay. All right, so I know we've been a couple of weeks since we last talked. We're on this chapter of special functions, and I think what we learned earlier was the radicals, the square roots, cube roots, and however number of powers radicals. And we also learned absolute value. Those are things that you learned at school. I think it's not that new, so I'm not going to go back and review them. So today we're going to start on floors and ceilings. These are going to be completely new functions that you will be introduced. Okay, so let's start. This is like these are very special type of functions that actually are pretty common in use. So this like rounding, right? So we can round up, like when it's 5 or above we round up, and when it's 4 and below we round down. That's like the rounding. Rounding is a general rule, but the floors and ceilings function can be considered a special rounding function. Okay, so this notation, actually, I don't know if this is like the universal notation, but flooring and ceiling is definitely a universal name. So this means it's a floor. Okay, what does it mean? It's like when we round, we disregard the size of the precision after the decimal place. As long as we, I guess when we do this, here in the book, we're talking about integers, but it's not just limited to integers. So let's start with integers. So if I have a number, say x equals to 3.5, the floor of this will be the greatest integer function of the greatest integer that's less than this. So the floor of x in this case will be 3. Okay, we just chop off everything after the decimal place. So in the book it says like the floor of 2.3. So normally when we round, we would round this as a 2.0, right? I mean, when we round it at 2.0. But when we round this, we round it up to 4.0. But when we have a floor function, it's only 3. Okay, so when it is an integer, it's itself. Okay, so basically you can see this as everything between 7.0 to 7.9999, like infinity. All of these numbers, when we floored it, would equals to 7. So all of this start from the number itself, 7.0, or any integer, to all the way, up to the very next integer will be a floor down to this same integer. Okay, so if it's a negative number, like say, for example, okay, so remember we're looking for the greatest integer function, and this goes the other direction. This can be tricky. So this is -6. So when we think about this, right, we look at the number line. So this is like -1, -2, -3, -4, -5, like 1, 2, 3, 4, 5, say 6. So any number on the number line here will be the next greatest number. So for this one, it'll be this one. For the number over here, it will be this one. Okay, so it's the greatest integer up to this point, up to the number. So you're looking for the greatest one. So when we look at the negative number, so over here, it's like -3.5, it's this number. So this is the floor. You can see it if we look at it. We put this on the vertical axis. If we draw the number line like this is where you can visually imagine the number. Yeah, right. So we just tilt this by 90 degrees. We have the same number. And the floor will be the number that's below it. So you can think of it as something that catches the number all the way above it, right? So all of these are the floors. So all numbers above it, like each one integer, there is a floor. imagine if you're dropping a like a tennis ball or table tennis, you're dropping a ball from the number axis, and at each integer tick marks, there is a floor to catch it, like floor number 1, 2, 3, 4. That'll be your floor. Makes sense? That helps you remember it. Okay. It just like when it comes to the negative number, it will be let's see. Okay. All right, so let's see. Let me give Yo-Yo the number. Okay. Let's see what the Yo-Yo can get in. Let's see. Meeting ID. Let me give her the number and we'll get started. Sorry, give me a second. Okay. All right, hopefully you'll be here soon. Okay, so this is the floor. Let's see if we okay, Yo-Yo. Oh, I guess that is the right one. Okay. Okay, at the same time, there's a symmetric function called seating, right? It's, we have this as the floor to catch it from above, below. Just think of like the apartment buildings in China, or large like high-rise buildings. There's floors, there's seatings, right? So now we have the seating, like this. This is a ceiling function. It goes similar to the floor, except it's the opposite in terms of it's the um, it's the integer, the smallest integer that's greater than the x. Okay, so this one is the greatest function that's smaller. That's the greatest integer. Yeah, that's below that's the greatest integer that's smaller than this. This is the largest integer, the smallest integer that's larger than this. All right, so basically what we can visualize is you now have ceilings, right? So basically it's the floor plus one. You're looking at the top, you're looking up. It's like as if you release a balloon, it will go on to the next one. So let's look at a couple of this. Say if x equals to 3.5 again, then the seeding of x will be 4. Okay, the seeding of 2.3 over here will be 3. It's the next greatest number. And the seeding of negative 5.3 will be negative 5. Okay, so you're thinking of, you can break this number line into little boxes, like, it's each one is a floor, and there's the bottom of the floor, there's the top of the floor, it's the seating and the flooring. Okay, and it's basically where you would put, so the number does not stay in the middle, like when we do the rounding, normal rounding, it goes up and down based on the midpoint. When we come to the floor and seating, it goes to the all the way to the top or all the way to the bottom. That's just that. There's nothing more to it than this, basically. Okay, so from there, let's just do some problems, right? So let's see, 20.12. Okay. All right. Let's see. AoPS, I don't think the let's see, did I give the right number? That's weird. Let me just copy the whole thing over. Okay. Yo-Yo is having a hard time joining the meeting, which is weird. I don't have Yo-Yo. Okay. Anyhow, so let's do some exercise on this. So this one, a floor of 2.7, that'd be 2. Okay. Seating of 3.5 would be 4. Okay. Floor of negative 2.3 would be negative 3. Okay. So the floor of 1, 2, 3 over 5, that would be 120 divided by 5, which is let's see, 24 equals to 24. Okay, this is the floor. Let's see. Okay. So this one actually equals to 24.6 if you calculate it out. So this one seating, oh, there we go. She's here now. Seating of square root of 39. Good morning, Yo-Yo. Hi. Sorry, it's you're having a hard time joining. We're talking about the special functions and we're talking about floors and seatings. Since I'm recording this, if you want, you can go back and watch the beginning. I'm not gonna repeat it. It's a new type of function, but it's actually pretty straightforward. So we're trying to do, you can also try to figure it out as we're talking through it. So, okay, when we look at this, what we can do, there's a couple of options. We can pull out the calculator and calculate this number out, right? But here's the thing. When we look at 39, we know it's not a perfect square. We know 36 is a perfect square, so square root of 36 equals to 6, which because 36 is less than 39, so we know a square root of 6 is less than 30, square root of 39. And we also know 49 is a perfect perfect square. So we know 39 is less than 49. So we know this number is between 6 and 7, right? For sure. And we're looking for the seating. So we really don't need to know the decimal numbers. We just need to know, where in which box this number belongs, right? So this one, we can just quickly say the seating of this number is 7 and the floor of square root of 39 is 6. Okay, so when you're doing actually in the test, this is a lot faster to what we call guesstimate than trying to figure out the exact solution. Hopefully that makes sense. And this last part, this part EF, is a double flooring. Okay, so it's the floor of square root of 3, 4, 5, floor, and then square root that again, and floor again. So this is nothing fancy. It's basically just apply it twice. So let's figure out what the square root, okay, let's do the first one. Okay, so let's figure out this step by step. When you see the nested function, don't be scared by it. That's nothing more than just, you know, just doing something twice. Okay, so this one, you may not know this like right off the top of your head, but this is something we can still guesstimate like what we did over here. So on this end, we say it's definitely 3, 4, 5 is less than 400. Okay, 400 is 20 squared. But there's like 55 between the two. So let's test it out and see 19 and see 19 squared if it's bigger or smaller than this number. So 19 squared, here's a quick way of estimating what 19 squared is. 19 squared equals to, this is kind of like a mental math, 20 minus 1. Okay, 20 minus 1 means if we do this, if you remember earlier we learned the factorization. So this is like a 400 minus 2 multiplied by 20 multiplied by 1 plus 1. So this is 401 minus 40. Okay, so this is 401 minus 40, so this is 361. It so happens 361 is between these two numbers, right? It pays to check. Actually, as you do this frequently enough, you would kind of estimate this. There's another number in between this, right? But I would say, you look at this, you look at the next round number, and then go from there. Okay, 19 squared, and then all we need to do is test 18 squared. 18 squared, similarly, we can say this is 400 minus 2 times 2 times 20 plus 4. Okay, so this is 404 minus 80. So that's 324. Okay, it so happens it's the next largest number. So this number is between 18 and 19. Okay, so the floor of this will be 18. Okay, so now the next step is to do this again. So the floor of square root of 18 is this actually be pretty straightforward. This is greater than 16, which is 4 squared, and less than 5 squared, which is 25. Okay, and in this case, what we care is about the floor, so the floor of this will be 4. Make sense? So this is how you can do math without calculators, by estimating, by getting closer to the answer without knowing the exact answer. Especially the nature of the flooring and seating functions, you only need to know the next integer, either the greatest or the smallest. Actually, the greatest integer less than the number, and okay, let me just repeat. The floor function is the greatest integer that's less than the number x. The seating function is the smallest integer that's greater or equal to this. Okay, so the greatest and the smallest are like in opposite positions. It can be a little bit confusing at first. That's why I'm thinking, if I'm saying, if you think about it visually like this, like, you're in the apartment building and you have a floor and seating, that's more intuitive than try to remember the definition of the function. So let's do 20.13. So we have f of x equals to floor of x, and g of x equals to seating of x, right? So this is basically the floor and seating of the function. Now we're doing the graphing, right? If I were to do, okay, so if I were to graph y equals to f of x, okay, so this actually becomes like steps, okay? All right, so let's do this. So for everything between 0 and 1, the floor of it will be 0 and 1. For everything between 1 and 2, it'd be 1. Everything between 2 and 3, it would be 3. And everything between 3 and 4, it would be 3 and 4. And over here, it would be this, and this, and this, and one last one is this. Okay, so this will be y equals to f of x. Make sense? And the floor, on the other hand, if we really want to be technical, we would say this is the closed end, this is the open end. You know, if you should remember from graphing from school, say if it's including this point, then it's the solid dot. If it's excluding, then it's an open circle. So the number actually is included. So I'm gonna probably do these just to be technically exact. Okay, open circle, 0 is over here. Okay, open and close and open and close like this. Okay, the floor ceiling happens to be just similar, except it's the floor. Okay, it's when it's between 6 and 7, you get 6. Okay, and it actually is open on this end and close on this end. Okay, so if it's between this, it's close on this end, it's open on this end. This is the floor function. Okay, open on this end. Okay, it's just so happens the floor and the ceiling function of the integer are both the integer itself. Okay, if you see over here, the 7 floor of 7 is 7, the ceiling of 7 is also 7. So this one be this one and this one and be this and this. Okay, so y equals to g of x. Okay, if you look at the graph, it's actually pretty straightforward, pretty simple. Makes sense? Okay, so 2014, for what value of x is ceiling of f of x equals to floor of x? I just said that for all of the integers, they are the same. Okay, if you, let's see, let's see if I can scroll this down. There's more problems. So this is the graph. I just graph it on the same picture over here, right? Our graph shows that the value of the integer are all integers, right? You can read it off the graph. Okay. Yeah, when x is not an integer, then this, you know, it's less than the floor but greater than the ceiling is somewhere in the middle. Oops, in the middle of the range. Okay. So x are integers. So these functions, because it disconnects and it's what we call piecewise function, it's not like a continuous line, so it has all these kind of a quirky properties that's different from before, right? Yeah, like I said, this can also denote the fractional part, right? So we can say this is the integer, and it's the curly bracket. So okay, so we're introducing a new function, curly bracket x. Okay, so what this is saying, this actually has a lot of use in computer science. When you do programming, actually, this is very useful. You want to separate out the integer part and the decimal number part separately. So when we do a curly bracket, we actually disregard all the integer part. We're only keeping the decimal place part. So for example, if we say curly bracket 3.4, this is equals to 0.3. If I do curly bracket 404.3, it still is the 0.3. So this doesn't matter how large your integer part is, because the floor ceiling can get to the integer part. This only gets to the what you call it, the decimal place part. Okay, so and if we were to do a negative number, so depending on the definition of the notation, this actually will be the 0.4. How do we get to 0.4? So this actually equals to, let's see, x equals to floor of x. Okay, so we are looking for the portion that's between the, so this and that, this and that. We're looking for the portion from once we have the floor and what's left over. Okay, so when it's negative number, you can just take the negative portion of the, oops. Oh, sorry. So negative portion 2. So this actually would be negative 5.6 minus negative 6, which gives you 0.4. Okay. So yeah. Okay. Or the other way you can think about it is x equals to the floor of x plus the decimal point of x. Okay. So this function nicely separated out into two parts, the decimal parts and the integer parts. Okay, so now we have this. Now we introduce this this new notation, and then this is our relationship, which we just work it out. When it's a positive number, it's the number. It's more straightforward. It's the decimal part and the integer part. When it's a negative number, you just have to be a little bit more careful. Just remember this definition. It's the floor, not the ceiling, plus the decimal number part. Okay. Hopefully that makes sense. Some problem involving tackled by, think of it, x equals to floor plus the decimal part. Okay, so then what we're trying to do is do some practice on this one, 20.16, so x plus floor of y. Okay, so a number, we have this. And, okay, oh, all right, sorry. We have this, we have to figure it out. So x plus floor y equals to 5.3, and y plus floor of x equals to 5.7. Okay, so now it's interesting, right? So how do we solve this? Okay, so we know x equals to this, right? So this means we have floor of x plus decimal part of y of x plus y, a floor of y equals to 5.3. Over here we have floor of y plus decimal point of y plus floor of x equals to 5.7. Now this floor of x, floor of x, floor of y is the same. So if we subtract the two, we know the difference between the or the sum, well, actually the difference between decimal point of y minus decimal point of x, okay, equals to this, the lower equation minus the upper equation, 5.7 minus 5.3, so 0.7. So we know the decimal point part of y is greater than decimal point part of x by 0.7. That's what we know, right? So then we can substitute. we can substitute the this, right? Let's see. Let's see. We have decimal point of sorry, the floor of x plus the floor of y, and we know this is integer, right? So when we add up the two, the decimal point actually of x equals to the decimal point of this, which is 0.3. The decimal point of this is, decimal point of y is 0.7. Okay, and the difference is 0.4. Okay. Now what we have is okay. I think we have 2 minutes left. Now we know is what the floor of x plus the floor of y equals to 5. Okay, from both of this. Okay, so okay, so this is what we know. This does not give us like a single solution, single point solution. Okay, so what we need to do is compute the number of ordered pairs that are everything looks make this and this are true. And because x and y are both positive, greater than 0, so we can start with x equals to 1.3 and 2.3. Oh, sorry, I should do it this way. So we're writing it in pairs, right? So we have 1.3, and when x part is 1, then this is 4.7. Then we have 2.3 and 3.7. Then we have 3.3 and 2.7. Okay. And then we have 4.3 and 1.7. So we have 4 pairs. Actually, sorry, we have more than 4 pairs. We have 0.3. This is still greater than 0, and 5.3. Oh, 5.7. Okay, and then on this side we have 5.3 and 0.7. It satisfies both x and y are greater than 0, and we have 1, 2, 3, 4, 5, 6 pairs of solutions over here. Okay, we're out of time, so I'm gonna let you go, and we'll come back and we'll talk about rational functions. So not relational, rational functions. Hopefully I'll close out this chapter today. Sounds good? I'll see you in 10 minutes, 10:20. Okay, sounds good. All right, I'll see you soon.